Hello, this is Miss Moore, and today during chemistry we're going to discuss periodic trends. So today's essential question: what is the effective nuclear charge? Really important concept here. And how does it affect the periodic trends? So let's start with a definition of a periodic trend. So what is a periodic trend? A periodic trend is a pattern. A trend in general is a pattern. And a periodic trend is a pattern found on the periodic table. Periodic trends can be seen going down a group due to the pattern in the valence electrons. Okay, so let's try that real quick just to make sure you've seen that. So if we try a few electron configurations for the group 1 elements, we'll do hydrogen, lithium, sodium. The electron configuration for hydrogen is 1s1. Lithium is 1s2, 2s1. And sodium is 1s2, 2s2, 2p6, 3s1. And I'll stop there. But you'll note that the valence electrons end in, all of them end in S1. And if we were to move on and look at the alkaline earth metals, beryllium, magnesium, calcium, etc., they'd all end in S2. And then the group 13 elements, boron, aluminum, gallium, etc., would end in S2P1 and so forth. So part of the reason for the periodic trends going down a group has to do with this pattern in their valence electrons. Periodic trends can also be seen on the periodic table going across a period. And the trends that we see going across the period are due to two things together. One is the addition of an additional proton, and at the same time we have an addition of an electron, importantly in the same energy level. So let's try a few electron configurations using period 2 elements. So lithium, once again, is 1s2, 2s1. Beryllium is 1s2, 2s2. Boron, 1s2, 2s2, 2p1. I guess we probably should do one more. How about carbon? 1s2, 2s2, 2p2. What you will note with the valence electrons is that we are adding one additional electron each time, but they're all in the same energy level. All right, periodic trends. Here, what I'm going to do is I'm going to list and define the different periodic trends that we are going to be discussing throughout the rest of the lecture. So, first we have atomic size. Atomic size is the size or radius of an atom. When we're talking about radius, what we mean is we're measuring the distance from the center of the nucleus to the outermost electron. Then we have ionic size, which is the size or radius of an ion. And we have ionization energy. Ionization energy is the energy required to remove an electron from an atom or ion. It's the amount of energy to make a positive ion or a cation. Okay? And removing an electron always is going to take energy. So when you see a number for ionization energy, it will always be a positive number. And before I move on, I will tell you that these three, atomic size, ionic size, and ionization energy, are extremely important for your AP exam. All right, next we have an electron affinity. Electron affinity is the measure of the energy change when an electron is added to a neutral atom or ion to form a negative ion. adding an electron usually releases energy, so the electron affinity, the number, is usually going to be negative. And the last periodic trend we're going to discuss is electronegativity. Electronegativity is the measure of the ability of an atom to draw bonding atoms to itself. It requires energy to hold an electron, so the number, the electronegativity number, will be a positive number. All right, before we start talking about the actual trends or patterns seen in the periodic table, let's talk about a couple things that underlie those trends. All right, and the first one is Coulomb's law. So Coulomb's law explains the attractions and repulsions between the charged particles. And here we're talking, the charged particles are the protons, which have a positive charge, and the electrons, which have a negative charge. So Coulomb's law says F equals K times Q1, Q2 divided by R2. So what in the world do those mean? F is the force, K is a constant, Q is the charge, and R is the distance between the two particles. Okay, and when we're talking about F, or the force, we're talking about the force of the attraction. You can think of it as the power or strength of the attraction. Okay, K is a constant, Q is the charge, and for us right now, when we're talking about the charge, we're talking about, it doesn't really matter which Q is which, but maybe Q1 might be the charge of the nucleus, and Q2 would be the charge of the electron. And it would be nice if I knew how to spell electron. And then R, the distance, we're talking about the distance between the nucleus, and usually the electron we're talking about would be the outermost electron. Something kind of interesting here too, or something you should understand, is when we're talking about the charge, what would be interesting is because the nucleus is all packed together, we're talking about Q1 again as the nucleus. We're actually talking about the whole nucleus, not the individual protons, versus the Q2, the electrons. We're basically normally talking about the electron under discussion, okay, the single electron, because the electrons are not all squished together, okay? Now, good news is you don't really need to, I don't believe I'm going to make you calculate anything with this formula, but understanding the formula helps you understand Coulomb's law, which will help you understand periodic trends. Okay? And this formula shows that as the distance between the particle increases, the forces decrease, right? So if the distance was 2, if the distance, let's say, was 2 something, I'm not really sure, versus if the distance was 4, being that we're dividing by the radius, that is going to decrease the force. So the farther away the electrons get from the nucleus, the smaller the force, the smaller the attraction on the nucleus to the outermost electron. Also, the formula also shows that as we add protons to the nucleus, right, if we have 2 protons, for, say, helium, or 3 protons for lithium, 4 protons, 5 protons, whatever, being that the charge is on the top, that is going to actually increase the force. So adding protons will increase the force or the power of the nucleus. But then if we add protons and add distance, it kind of gets all complicated in there. But there you go. That's what you need to know for the moment about Coulomb's law. The next underlying reason for periodic trends is something we call the effective nuclear charge, which may not be the same as the actual nuclear charge. So the effective nuclear charge is how much power the nucleus has on an electron. Okay? And why it's called effective nuclear charge as opposed to just nuclear charge is the effective nuclear charge is the actual nuclear charge minus the charge screened by other electrons. Okay, so let me kind of show you an example. We'll use lithium. Lithium's nice and easy. Lithium has 3 protons and 3 electrons. Its electron configuration is 1s2, 2s1. And if we're interested in the valence electrons, we're talking about this electron here. So its effective nuclear charge equals the actual charge, which is 3, minus the charge screened by other electrons. There's 2 electrons between the nucleus and the outermost or valence electrons, so it'd be 3 minus 2, so the effective nuclear charge is 1. If we move across the period and now talk about beryllium, so beryllium has 4 protons and 4 electrons. So his electron configuration is 1s2, 2s2. Valence electrons here. So if we're interested in one of those valence electrons, its effective nuclear charge would be 4 minus the inner core electrons again, which is 2. So now the effective nuclear charge is 2. So even though we added both an electron and a proton moving across a period, we did not change energy levels, right? So there's no extra electrons between one outer electron and the nucleus, so the effective nuclear charge goes up. If we were to instead go down a group, so we'll go from lithium now to sodium. And sodium has 11 protons and 11 electrons with an electron configuration of 1s2, 2s2, 2p6, 3s1. The valence electron we're interested in is 3s1. So effective nuclear charge equals, we have 11 protons minus the protons in between the nucleus and the valence electron we're interested in, which is all of these guys here, and that is 10. So the effective nuclear charge is still 1. Even though there's a whole lot more protons and a whole lot more electrons, because of all of these inner electrons, we end up with the same effective nuclear charge. Okay, let's talk about the different trends now, keeping in mind the 2 underlying reasons for the trends, Coulomb's law and effective nuclear charge. We'll start with atomic size. So in general, the size of an atom increases going down a group, meaning the atom gets bigger and bigger as you go down a group, and decreases going across a period. All right, and before we move on, it's really important. Please, please, please don't try to just memorize this. It will not help you on the test. What you need to do is you need to understand why. Hugely important. Okay, so going down a group. As we move down a group or column in the periodic table, the actual nuclear charge increases, but the effective nuclear charge does not, which means there is actually no increase in the effective nuclear charge. And that's something we just talked about. But what does happen? Well, if we look, we just did this here between lithium and sodium. What happens is that we go up an energy level, right? We go from 1s2, 2s1 to 1s2, 2s2, 2p6, 3s1. So there's no change in nuclear charge, but there's an increase in energy levels. And remember, as you add an energy level, you're moving farther from the nucleus. So what does that mean? That means a bigger atom. So at the same time, the distance between the charge of the nucleus and the outermost electrons increases. Again, why does it increase? Because we're going up in energy level. Or maybe a better way to say that is we're adding an energy level. Okay, so at the same time, the distance between the charge of the nucleus and the outermost electrons increases, so the force holding the opposite charge together decreases, leading to a larger atom, right? And this point B has to do with what? Coulomb's law. Now, let's talk about going across a period. Remember, the atom gets smaller as you go across a period. Why? As we move across a period or row in the periodic table, the actual nuclear charge increases, and the effective nuclear charge increases as well. We also just talked about that. Let's go check it out. Okay, so here, going across the period, we're discussing lithium and boron. And what you see is that, and you know what? After all of this time, I just realized this should not be boron, right? This is beryllium. Anyway, okay, we're discussing lithium and beryllium. And what we see is that we're adding protons and electrons. But because we're adding electrons to the same energy level, we're not changing the energy level, so we're actually increasing both the actual nuclear charge and the effective nuclear charge, right? We're going from an effective nuclear charge of 1 with lithium and an effective nuclear charge of 2 with beryllium, not boron. At the same time, the distance, the radius, right? The radius, the distance between the charge of the nucleus and the outermost electrons remains the same, so the force holding the opposite charge together increases, leading to a smaller atom. So if we use our lithium beryllium example, right, we had force equals how many, Q1 we'll call for our protons. We had for lithium, we had a force of 3 positive, and electrons 3 negative, and a radius, I have no idea, let's just say it's 2. And then for boron, beryllium, why do I really want this to be boron? I have no idea. Force equals now plus 4. Electrons are 4, but the radius is still 2. Right? So we're going to end up with a larger force. All right, on to ionic size. And ionic size is takes a little bit more thinking than atomic size. So here we go. The periodic trend in ionic size or radius is different if we're talking about cations or anions. Okay, so let's start with cations. Cations are smaller than their corresponding atoms because of the removal of an electron leads to a larger effective nuclear charge. Let's go through this. We'll use lithium again because lithium is just so easy, right? So we have 1s2, 2s1. That's the lithium atom. How does lithium become an ion? Well, lithium ion is a plus, and it removes 1 electron. It's going to be 1s2. So now if we were to look at the effective nuclear charge of lithium, the nuclear charge is 3, right? 3 protons minus the core or inner electrons, which is 2. Whoa, that's not a 2. Let's try that again. Minus 2 gives us an effective nuclear charge of 1. How about for lithium ion? Lithium ion effective nuclear charge equals, it still has 3 protons, right? And it now has no inner electrons. So the effective nuclear charge is now 3. Being that the nucleus is now stronger, effectively stronger, right, at the outermost electrons, it's going to pull that atom closer, the electrons closer together, leading to a much smaller particle. Okay, I hope that makes sense. Okay, so now what is the trend going across a period? Going across a period, the ionic size of cations decreases because you're actually losing more electrons, but at the same time, there's more and more protons, right? Because lithium has 3 electrons and 3 protons. Lithium ion has 3 protons and 2 electrons. Okay, this is not going to work. So let's look at this. Lithium ion has 3 protons and 2 electrons, right? It's a 1+. Whereas beryllium ion is a 2+. It has 3, nope, it doesn't have 3. It has 4 protons and how many electrons? Still only 2 electrons. So you can see that beryllium is going to be even smaller. Because if you do the math, the effective nuclear charge is even greater. If we were to go on to boron would be B3+. So we can keep going. You sort of get the point, right? Okay, so going across the period, the ionic size of cations decreases because more electrons are removed and each ion has 1 more proton than the previous one, leading to a greater effective nuclear charge. Okay, let's talk about anions and ionic size. So anions are larger than their corresponding atoms because of the addition of electrons leads to a smaller effective nuclear charge. So if we take, for example, fluorine atom has 9 protons and 9 electrons with an electron configuration of 1s2, 2s2, 2p5. And then fluorine ion still has 9 protons. Protons don't change, but it now has 10 electrons. It needs to gain 1 electron to have noble gas configuration. So 1s2, 2s2, 2p6. So now fluorine has 9 protons for 10 electrons. That's a weaker nucleus compared to the number of electrons. So that means it's going to be larger. If we were to take oxygen, oxygen is O2 minus, right? So he's going to be 1s2, 2s2, 2p6 as well. However, oxygen only has 8 protons and still 10 electrons. So of these two, even though they have, of these two, meaning fluorine ion and oxygen ion, even though fluorine ion and oxygen ion both have 10 electrons, fluorine has 9 protons, oxygen has 8 protons, right? So between those two, fluorine ion is going to be smaller, has a stronger nucleus. So going across the period, the ionic size of anions also decreases because less electrons are gained and each has an additional proton, leading to a greater effective nuclear charge. Okay, here's something interesting to think about as well. Let's take neon and two ions that are isoelectronic with neon. We'll take fluorine and sodium. Let's try to rank those by size. So neon has 10 protons and 10 electrons. Fluorine has 9 protons, fluorine ion, 9 protons and 10 electrons. Sodium ion has 11 protons and 10 electrons. So which one of these is going to be the smallest? The one that's the smallest is the one with the strongest nucleus, which would be neon. Sodium. So sodium is the smallest. And then which one would be the largest? The largest would be the one with the least number of protons, which would be fluorine ion. I should have made this an ion. So fluorine ion will be the largest because it has the weakest nucleus. Okay, so there's a lot of thinking involved in ionic size. So really, really make sure you understand the reason why. That will help. Okay, on to ionization energy. Remember that ionization energy is the energy needed to remove an electron from an atom, making it a positive ion. So the first thing I want to do is give you a list, an example of some ionization energies of aluminum. Okay, so here we have aluminum, right here, losing 1 electron to become Al1+. And then we can have aluminum 1+ losing another electron to become aluminum 2+, and so forth. Okay, so aluminum, it has, well, let me draw so we have aluminum, which is 1s2, 2s2, 2p6, 3s2, 3p1. The valence electrons aluminum would lose to become like a noble gas are these 3. So now look at the ionization energies. To remove 1 electron, it takes about 580 kilojoules per mole amount of energy to remove 1 electron. To remove the second electron, 1815, and then to remove the third, 2740. You will note that those are kind of like doubled, right? To go from 580 to 1850, doubled-ish, more than doubled, but in that range. And then to remove the third. But then look, once you go to try to move one of the core electrons to get to Al4+, there's a huge jump in the amount of energy. Why is that? It goes back to effective nuclear charge. The effective nuclear charge for the valence electrons, we've got 13 protons minus the core electrons, right? These guys here, which is 10, is 3. So for all 3 of the first electrons removed, the valence electrons, the effective nuclear energy is, or effective nuclear charge is 3. So it's hard to remove them, and it gets harder as you remove more because you have an unequal number of protons and electrons. But then what happens if we try to jump down and remove an electron here? So these guys are now gone. So effective nuclear charge, the nucleus still has 13 protons, but now our valence electrons are in the 2 range, right? So the core electrons is going to be just the 1s2, so it's going to be -2. So the effective nuclear charge is now 11. which is way, way more, which is why it's so much harder to remove electrons that are not valence electrons. Okay, now let's talk about the periodic trend in ionization energy. So in general, ionization energy decreases going down a group and increases going across the period. Once again, please don't just memorize that. It's super important that you understand why. Okay, really, really important. So here we go. Going down a group, as we move down a group or column in the periodic table, we've already talked about this, the actual nuclear charge increases, but the effective nuclear charge does not. And at the same time, the distance between the charge of the nucleus and the outermost electrons increases. Coulomb's law, again, we went over this. So the force holding the opposite charges together decreases, so the valence electrons are not held as tightly, making it easier to remove an electron. All right, how about going across a period? As we move across a period or row in the periodic table, the actual nuclear charge increases, right? And the effective nuclear charge increases as well. We are adding both a proton and an electron as we move across the period, but the electrons being added into the same row, no more core electrons block shielding, which leads to an increase in effective nuclear charge, which means the atom is going to hold its outermost electrons tighter. At the same time, the distance between the charge of the nucleus and the outermost electrons remains the same, but the charge on the nucleus increases, so the force holding the opposite charge together increases, leading to more tightly held valence electrons. Okay, so these reasons are exactly the same as the reasons for ionic size and atomic size. And then the last topic, and this is going to be one sentence, we're almost done here, is electron affinity and electronegativity. Good news is the periodic trends for electron affinity and electronegativity are the same as those for ionization energy and for the same reasons. All right, so before I say goodbye, I want to remind you, make sure you understand why for everything. Okay, think about Coulomb's law and effective nuclear charge. Okay, that is hugely important. Okay, folks, sorry for the long lecture. That's it for today.